section basically says it's a distance from the reference axis, x or y, at which the entire area is located without changing its moment of inertia. It's the distribution of components of an object around an axis. And it's useful in determining the stiffness of a column. The formula for that, oops, I guess one thing I didn't turn on. Is the radius of gyration, and that's just signified by a lowercase r. That looks like crap. Is equal to the square root of the moment of inertia divided by the area. And that's based on the respective axis. So it would be, if you're dealing with the radius of gyration for the x-axis, then you would use the xx values, if you will. Of course, the area is going to be the same. Based on that, we're not going to get too worried about this as far as what we have to do. Well, after you find the moment of inertia and you've already gotten the area, right? You had to. You plug those two numbers in and you get your answer. Okay, and you'll be using that in later chapters as part of your calculations. Okay? Now, then, and that's as far as I want to go with that. I don't even know that there are some examples. There's an example on page 168, but it's just plugging in numbers that you already have figured out. Now, again, if we do that on a test, and you figured out the moment of inertia incorrectly, but you showed your work, at least you're going to get the points for showing your work and having that. Even though the number's wrong, you'll still get some points for it. So just keep that in mind always. Okay? Because, you can see where if you get one number wrong, it's going to screw up everything in it. Your numbers all the way throughout are going to be wrong at this point, but you're still going to get credit for having done the work properly. You just had the wrong number in there. Okay? Jabril? Well, yeah, it would be the total area for the whole thing. Yeah. So if you had holes in there, you'd have to subtract them out. Yeah, it's the area of that first picture you deal with. Okay? Yep. Now then, the polar moment of inertia, if we look at that, that is calculated with respect to the axis perpendicular to that plane that you're dealing with. And I've got a note there, look at figure 815. Let's see, that's the one thing I didn't get started here. Sorry about that. Got to get that. Let's see here. Don't need that anymore. Okay, polar moment of inertia, dealing with that right there. That, again, calculated with respect to the axis perpendicular to the plane. That would be the z-axis. Okay, and that's typical. So you're looking for that point right there. And that could be anywhere around there. How do we calculate that? And again, and I saw something, let's see. Yeah, note, and we have to use table 3, and I think I made copies of that and gave them to you, I believe. And by the way, Zach, I don't think you got those. I don't think you got a copy of this. It's table 2 and 3. But it says, if you note there on page 164, the polar moment of inertia of circular members is a property required for the solution of problems involving shafts subjected to torsional loads. So we'll be dealing with that, and that'll be in chapter 12. Okay, but at least we're going to learn how to calculate those here. So that's And let's see, I don't know if I check something here real quick. I don't know if I made a copy of that particular. I don't think I did. I was wondering if I made a copy of that particular picture, but I didn't, so we'll just sketch it in there. Figure 8.16, the hollow shaft there on page 169. It says calculate the polar moment of inertia for a hollow circular shaft with an outside diameter of 4 inches and an inside diameter of 3 inches. Okay, so the polar moment of inertia and note, I guess I skipped over that. On page 169 at the top, there are a couple of equations. We've got the polar moment of inertia, which is signified by a J, is the summation of the areas times x squared plus y squared. And note then what they tell you is that also then gets transferred into the summation of a times x squared plus a times y squared. My writing is terrible today, I apologize. So we've got, but it says with reference to equations 8, 1, and 2, this equation may be written as the polar moment of inertia is equal to the moment of inertia of x plus the moment of inertia of y. So when we look at this problem, we've got that hollow shaft, and this is where we could remember we were talking about the drive shaft the other day, where we could prove out that we get better results from that large diameter skinny cross-sectional area as opposed to the thicker. So we've got outside diameter of 4 inches and inside diameter of 3. That looks like crap. Now, normally I would put a plus symbol and all that in there and make it look like a real drawing. I'm not going to do that right now. So, the polar moment of inertia with respect to the center of gravity, which is probably what you're going to do for the most part, is the area, right? That's or is this, yeah, from table 3. Let's see, let's go back. I think it, didn't I have table 3 on this?
Yeah, you did.
Yeah, table 3. So if you look at the polar moment of inertia for a circular piece, it's pi times the diameter cubed divided by 32, right? For one particular circular feature. So it would be pi times the diameter cubed divided by 32 for the 4-inch piece minus pi times the diameter cubed divided by 32 for the 3-inch piece, right? So when they wrote the problem, they did this. Polar moment of inertia with respect to the center of gravity is pi over 32, which is common for these, right? Times the diameter of 4 cubed minus 3 cubed, or excuse me, thank you, to the 4th power. Cubed would be 3, wouldn't it? Okay? Punch that into your calculator and you should end up with 17.18 inches to the fourth, right? Not cubed. Catch me saying that again. That won't be the last time I'll say that, probably. We can deal with cubed, right? It's volume. That's something we know. To the fourth, it's like, where's that other? We're dealing with another dimension. And it's Friday. Thank goodness. Although that just means I'm going to have to work hard this weekend. 3 days this weekend. When I come in here Wednesday, I'll probably be dragging. That's not too difficult, in my estimation. I mean, you're going in, you're using the table that's supplied. That's just a copy out of the book. Okay, and punching in the numbers. Again, make sure that you can go in there and punch that in your calculator and come up with that answer. If you can't, then you better get some help so you can. So you'll be ready for a test. Because, again, from my perspective, that's just plugging a bunch of numbers in to a formula that's already there. There's not a whole lot of brain power having to be used up there, which means that ought to be easy points on a test. Okay? The first part of that is this part right here. Just doing this part right here. My goodness. That's just copying down a formula, and you're going to get points for that. Then if you screw this up, I'll take points off, but it's because you didn't use your calculator. So if you practice it, you'll be able to. See, I personally think I'm being too easy on you when I'm grading, because I'm going to give you points for just writing that in. Or even on those other tests, I just gave you points just for writing the word KIP down. See, I think that's being pretty gracious by giving you those points. Or the direction. Shame on you if you forgot to write them down. Can lead a horse to water. About the size of it. Now, I did want to show you